Hello everybody, my name is David Pitanes and I am going to be solving Griffiths Problem 2.12. It asks us to do the following. To use Gauss's law to find the electric field inside a uniformly charged solid sphere of charge density rho, and to compare our answer to problem 2.8. Well, the first thing we're going to want to do is to write out Gauss's law, which is the closed surface area integral of the electric field times the dot product of the area element. And this is going to be equal to the charge enclosed, which we're going to call little q enclosed. And this is going to be written over epsilon naught. So to get a better idea of what we're going to be doing, I'm going to make a circle just as like a representation of our solid sphere. And so this is going to be our sphere right here. And since we want to find the electric field inside of the uniformly charged solid sphere, we're going to make a little Gaussian surface. Now, my circle may not be perfect, but I think it gets the point across. And so another thing we're going to have to do is we're going to have to make our actual solid sphere have a radius of big R, while our Gaussian surface is going to have a radius of little r, just so we can differentiate between the two, because they're not going to be the same radiuses. So now that we've done that, the next step in this process is going to be trying to figure out what Q enclosed is. And since we're working with a solid sphere, then we should know that Q enclosed is going to be equal to the charge density rho times the volume element d tau. If we were working with a shell, then it would have been sigma times the area element, but since we're working with a solid sphere, this is what we're going to be using. So now that we have this written out, we're going to plug this back into here, and that should give us our next step of the equation. I'm going to try to see if I can do something to make writing less. So we have this, and then I'll simply copy this over. Set these two equal to each other, and have epsilon naught here. Now, another thing I'm gonna do is I'm gonna try to take the electric field out of the integral, so that we just had to do a surface integral for the Gaussian surface. The argument I'm going to make is that the electric field of the sphere is pointing radially outwards in every direction, right? This is one E component, or like one electric field that's pointing out. This is another one pointing out radially outwards. It's important to note that they have the same magnitude, so you wouldn't be able to tell which one's which if you were on the inside, right? To be more specific about that, picture that you're inside of the sphere. You look south, west, north, east, any direction really. You would look at this electric field, right? Or you would look at this electric field, and you wouldn't be able to tell them apart. You wouldn't be able to tell, hey, is that going up, down? You wouldn't know. And so because of that, we can treat the electric field instead of a vector as a magnitude, right? And since it's also uniformly charged, the solid sphere, we're able to take it out. And so now we're just left with a surface integral of our Gaussian surface. Furthermore, we also know that, the charge density, rho, is also uniform, or because the sphere is uniform, rho is constant. So we can also pull that out of our integral that we're going to have on the right side. That also includes epsilon naught. And so we're going to be taking the volume integral of the sphere, or the charge enclosed within this Gaussian surface, which is like the solid sphere, right? So basically, we're just going to take the integrals, which shouldn't be too hard. We know that the surface area of a sphere is equal to 4 pi r squared. And we're going to set this side equal to rho over epsilon naught times the volume of the sphere, which we all know is 4/3 pi r cubed. Now that we have this, all we have to do is a little bit of algebra and we will get closer to our answer. So we have the 4 on both sides, we cancel that out. We have pi's on both sides, we cancel that out. We cancel the r's on this side, we just reduce the r's on this side. We're going to isolate the e, get it by itself. We're going to do a little trick called copy pasting this part onto the other side. And the only things we're really left with at this point is the r right here from the volume side and the 3, the denominator. And so we're almost done with our answer. We just need one more thing, which is the fact that the electric field is a vector and not a magnitude. And although we use the argument that we can treat it as a magnitude, at the end of the day, when you want your answer, you want it as a vector. So this is going to lead us to the following. We have to figure out in what direction the electric field is pointing. And as I stated earlier, the electric field is pointing in the r hat direction because it's pointing out radially. And so with that, we can safely put the vector hat on top of the electric field. And this is going to be the answer to our first part of 2.12. Now, we mostly solved the problem, but now we have to compare our answer to 2.8, right? And to do that, we have to do the following. 2.8 puts their answer in terms of total charge, right? And we have our answer in charge density. So we're going to have to remedy the two. We know that the total charge is equal to rho times the volume element. Now, the difference between this volume element and the other volume element is that when we were trying to find the charge enclosed inside of our Gaussian surface, right? This time, we're finding the charge enclosed in all of the solid sphere. And so, when we're getting our volume for the sphere, instead of using little r like we did here, we're going to be using big R. And so we are going to get rho times 4/3 pi big R cubed. And so all of this is equal to, I'm going to just abbreviate this to Q because writing the total part is a little hard. So now we have this. We're going to do a little bit of algebra just to isolate the rho. And so when we isolate it, we're going to get Q over 4 pi r cubed. And we can't forget the 3 on top. And so now we have this. What we can do is we can get our little equation right here. We can copy it over. And instead of having the rho here, we can plug in rho. Yeah, so we're just going to drag this over here. Plop it down right there. I'm going to do a little bit of algebra, which is just canceling out the 3's right there and there. And now I'm going to actually just rewrite it because this electric field looks a little sloppy with copy-paste. But what we should be getting is the following. Your electric field is equal to the total charge Q times a little r. And all that is over 4 pi epsilon naught times big R cubed. There we go. And we just need to write one more thing, which is our hat. And with this, we have a way to compare our answer to problem 2.8. So this is how you'd solve Griffiths problem 2.12. My name is David Pitones, and I hope you learned something today. Thank you for watching.